Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, we will discuss about the problems on crystal structures. So, the first problem is calculate the number of atoms per unit cell of a metal with lattice parameter 2.9 angstroms, and then the molecular weight is given as 55.85 kilogram per meter cube, and the density is 7,870 kilogram per meter cube, and Avogadro's number is 6.023 into 10 power 26 kilomole inverse. So for this problem, we'll solve by taking the given data. So the given data is lattice parameters as given in the problem, the lattice parameter which is denoted with A. So A is equals to 2.9 angstroms. So that is here the lattice parameter A is 2.9 angstroms. So angstroms is converted into meters. So 1 angstrom is equals to 10 power minus 8 centimeters when it is converted into meters. So 2.9 into 10 power minus 10 meters. Okay, so 1 angstrom is equals to 10 power minus 8 centimeters when it is converted into meters, 10 power minus 10 meters. So lattice parameter A is equals to 2.9 angstroms, that is equals to 2.9 into 10 power minus 10 meters. And the molecular weight given as 55.85 kilogram per meter cube. Already it is the same units, and the density rho is equals to 7870 kilogram per meter cube. And the Avogadro's number is given by Na is equals to 6.023 into 10 power 26 kilomole inverse. So these are the data given in the problem. So we want to calculate the number of atoms per unit cell of a metal. So we need to calculate the number of atoms. The number of atoms per unit cell of a metal. This is that we need to calculate. So for that, we have an expression for the lattice parameter. So A is equals to Nm by rho into Na whole power 1 by 3. So here A is the lattice parameter, N is number of atoms per unit cell, and M is the molecular weight, rho is the density, and Na is the Avogadro's number. So from this, we need to calculate N because lattice parameter N is given in the problem, but we need to find number of atoms. So from this expression, N is equals to rho into Na A cube by M. So here we can now derive A is equals to Nm by rho to Avogadro's number whole power 1 by 3. This implies we need to find N value so that A cube is equal to Nm by rho Na. It is equals to, that implies A cube rho Na is equal to Nm. But we want N number of atoms per unit cell. So N is equal to N is equal to rho N A cube by capital M. So this is the formula which we derived from the simplified from the A. Okay, so this is the number of atoms per unit cell which is get from the A. Then the number of atoms per unit cell n is equals to, by substituting all these values, so the value of rho is equals to 7870 kilogram per meter cube, and then the Avogadro's number is 6.023 into 10 power 23, and then a cube is 2.9 into 10 power minus 10 whole cube, so divided by the molecular weight, so 55.85 kilogram per meter cube. So when simplifying this n value, will get 2.06, so that is equals to, it has the number of atoms per unit cell is 2. So 2 atoms per unit cell. Okay. So the number of atoms per unit cell n is equals to 2. Next problem. Chromium has BCC structure. So BCC structure means body-centered cubic structure. So chromium has body-centered cubic structure, and this chromium has atomic radius 0.1249 nanometers. But calculate the free volume per unit cell. Free volume per unit cell. So solution for this problem, let's write the given data. So the given data is atomic radius of the chromium body centered cubic structure R is equals to 0.1249 nanometers. So nanometers is converted into meters. So 1 nanometer is equals to 10 power minus 9 meters. So it is equals to 0.1249 into 10 power minus 9 meters. So we need to calculate free volume per unit cell. So the free volume per unit cell of BCC is equals to 0.32 into A cube. 0.32 into A cube. So what is the value of A? What is the value of A? So from the relation between R and A in BCC is R is equals to root 3A by 4. So body centered cubic crystal structures radius R is equals to root 3A by 4. So from this we'll get the value A is equals to 4R by root 3. So for BCC system, R is equals to root 3A by 4. So from this, A is equals to 4R by root 3. So substituting the values of R, so R is given in the problem. So 4 into 0.1249 into 10 power minus 9 divided by root 3. Okay. So it is equals to the value of 2.884 into 10 power minus 10 meters. So therefore, A free volume per unit cell is equals to 0.32 into A cube. So we found A value. A is equals to 2.884 into 10 power minus 10 meters. So free volume of BCC is 0.32 into A cube. So substituting A value, so 2.884 into 10 power minus 10 meters will get a whole cube. So we'll get 7.676 into 10 power minus 30 meter cube. So this is the value of free volume per unit cell. Next problem. So the copper has a FCC structure and the atomic radius is 1.278 angstroms. Calculate the density of copper crystal given atomic weight of copper is 63.5. So FCC means face centered cubic structure. So copper has FCC structure with atomic radius 1.278 angstroms, and given the atomic weight of copper is 63.5. So calculate density of copper crystal. Density of copper crystal. So density rho. We need to find rho. So to get the solution, first write the given data. So the given data, first atomic radius has given, and then the atomic weight m value. So atomic radius 1.278. 1.278 angstroms. So it is converted into meters. So 1.278 into 10 power minus 10 meters, and atomic weight m is equals to 63.5. So for FCC, the relation between R and A is R is equals to, for FCC, R is equals to atomic radius, R is equals to A by 2 root 2. So from this, A is equals to 2 root 2 R. So R is given. So substituting R value. So R value is 1.278 into 10 power minus 10 meters. So A is equals to 3.614 angstroms. If we convert it into the same, if we are calculating in angstroms, it would be comes in angstroms. If we need to calculate, if we converted into meters, it would come into meters itself. So A is equals to 3.614 angstroms. So if we get here, the value will become different. Okay, so here I've written the A value, lattice parameter. A is equals to 3.614 angstroms. So in angstroms, I've calculated. So the lattice parameter we got here is 3.614 angstroms. And Avogadro's number Na is equals to 6.023 into 10 power 26 kilomole inverse. Now we have A is equals to lattice parameter. A is equals to Nm by rho Na whole power 1 by 3. So we need to calculate the density of copper crystal. Here we need to find the density of copper crystal. So to find this, we use the formula A is equals to Nm by rho Na whole power 1 by 3. So from this, rho A is equals to Nm by rho Na whole power 1 by 3. So from this, rho is equals to Nm by Na AQ. So substituting the values. So here I am substituting the value, the molecular weight and everything. So we'll have the value, we will get the value 8.92 into 10 power 3, 10 cube kilogram per meter cube. So which is in meter cube, written in meter cube. So rho is equals to n number of atoms, n value, and then into the weight of the unit cell, molecular weight, divided by Avogadro's number, then A cube, it is equals to, simplifying this, we'll get the value 8.92 into 10 cube kilogram per meter cube. Next, show that in a simple cubic lattice, the separation between successive lattice planes separation is 1 0 0, 1 1 0, 1 1 1, or in the ratio 1 is to 0.71 is to 0.58. Okay. Show that in a simple cubic lattice, the separation between successive lattice planes 1 0 0, 1 1 0, 1 1 1, or in the ratio 1 is to 0.71 is to 0.58. So the solution for the problem is, first we will write the data which is given. So lattice planes given in this problem is 1 0 0, 1 1 0, 1 1 1. So we need to show the simple cubic lattice separation between successive planes in the ratio 1 is to 0.71 is to 0.58. So the separation between the successive planes, we have the formula D is equals to A by root of H square plus K square plus L square. D is equals to A by root of H square plus K square plus L square. So here for the plane, first lattice plane, that is D100. So it is equals to A by root of H square is 1. So 1 square, Y is, Y means here H, K, L. So H is 1, K is 0, L is 0. Let's substituting A by root of 1 square plus 0 plus 0. So A by root 1. So it is equals to A. For the second plane, D110, it is equals to A by root of HKL. So H is 1, L is 1 and L is 0. So A by root of 1 square plus 1 square plus 0. So it is equals to A by root 2. And for the third plane, third lattice plane, D111, it is equals to, this is 1. So here HKL, so it is equals to A by root of 1 plus, 1 square plus 1 square plus 1 square. It is equals to A by root 3. So we need to show this D is in the ratio of 1 is to 0.71 is to 0.58. So D100 is to D110 is to D111 is equals to 1 is to 1 by root 2 is to 1 by root 2. That is, here we got the value D100 is equals to A. That is equals to, when we are taking a ratio, so it will become 1. So D110 is equals to A by root 2. D111 is equals to A by root 3. So when taking ratio, D100 is to D110, D111 is equals to, D is nothing but separation between the successive planes or distance, interplane or distance between the parallel planes. It is equals to A by, A is to A by root 2 is to A by root 3. It is nothing but 1 is to 1 by root 2 is to 1 by root 3. Okay. So these values are 1 is to 0.707 is to 0.577. It is nearly 0.58. So this is the value which we have to show in the simple cubic lattice. So the next problem, find the Miller indices of a set of parallel planes which makes intercepts in the ratio 3a is to 4b on the x and y axis and are parallel to z axis. A, B, C being primitive vectors of the lattice. So find the Miller indices. So we need to find the Miller indices of a set of parallel planes which makes intercepts in the ratio 3a is to 4b on the x and y axis and are parallel to z axis. So A, B, C being primitive vectors of the lattice. Okay, solution is given that the interceptions. So interceptions have been given for x and y, and for the z axis they are parallel to z axis. Okay, so the intercepts 3a is to 4b. If plane is parallel to axis, then the corresponding intercepts is infinity. So if the plane is parallel to the axis, then the corresponding intercept is infinity. So the third one, z-axis, is the third interception is, that is here in the problem, intercepts have been given for x and y axis, but for the z axis it is parallel to this x and y. So that what happens here, as it is parallel to the plane, so that the interception is infinity. The interception on z axis is infinity. So that's why when taking the interception ratio, p is to q is to r, that is equals to 3a is to 4p is to infinity. Okay, as the interceptions are 3a, 4p, but the third one interception is infinity because it is parallel to the axis. So HKL, HKL, H is to K is to L is equals to 1 by P is to 1 by Q is to 1 by infinity. So it is equals to the ratio of 4 is to 3 is to 0. As in finding the Miller indices, first we have to take the integers. Okay, so then we have the different steps in the Miller indices already we have discussed in the previous sessions lecture. So from that we have to take the integers of the integer multiples of the lattice parameters. Then we need to take the reciprocals, and then we have to convert it into integers by taking the LCM. Then we have to indicate in the parenthesis. Okay, so here the values are 3, 4, and then infinity. So then we have to take the reciprocals 1 by 3, 1 by 4, and 1 by infinity. So then we have to take it into integer value. So by taking the LCM, so that we'll get the value 4, 3 is to 1 by infinity is 0. Okay, so we have to indicate this one in closed brackets. So this represents the Miller indices. Okay, so first we have to write the interceptions on all the three axes. So the interceptions of the two axes is at 3 and 4, at 3a and 4p. But the third axis, it is parallel to the plane, so that we have written infinity. Okay, so the multiple of this a is 3, 4, infinity. So then in the second step, we have to take the reciprocal. Then we have to convert into integers. That is, we have to do the LCM. So 4, 3, 0. Then indicate with parenthesis. So this gives the Miller indices of the given problem. So the next problem is, in a triclinic crystal, a lattice plane makes intercepts of lengths a to b and minus 3c by 2. Find the Miller indices of the plane. In a triclinic crystal, a lattice plane makes intercepts of lengths a to b and minus 3c by 2. Then find the Miller indices of the plane. So solution is, given that interceptions. So interceptions are a to b minus 3c by 2. So p is to q is to r is equals to the multiples of the lattice parameters is 1 is to 2 is to minus 3 by 2. Okay, so then HKL, H is to K is to L is equals to 1 by P is to 1 by Q is to 1 by R. So that is equals to when taking a reciprocals. So first we have to write the interceptions. That's why we have written here intercepts on the 3 axis. So minus 3c by 2. So the intercepts, that is multiple of A is 1, B is 2 and C is minus 3 by 2. Then we have to take the reciprocals. So that 1 by 1, 1 by 2 and then 1 by minus 3 by 2. So then convert it into integer part so that it would come 6, 3 and then minus 4. Then indicate with closed parenthesis. So minus 4 means invert. Okay, invert. So 6, 3, inversion of 4. Okay, so this is the Miller indices for the given problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.